All right, let's get started. So we were working with the basic definition for velocity. We defined average velocity. Average velocity is the total displacement. Displacement is the shortest distance from one point to another point. So when you divide that displacement by the total time elapsed in order to do that displacement, that velocity or that quantity is called averaged velocity. It's called average velocity because it's being divided by the total time. You want to know how much distance will be covered per second, per unit time. That definition is for any interval of time. However, that does not give you the value of speed or velocity at a one time value at any instant. You don't know what the velocity going to be at any instant. For that, you calculate instantaneous velocity. This is mainly a calculus concept. Okay, since we cannot cover calculus here, we do need to understand it in terms of change in position with respect to time in the very small interval. So you can consider that you have divided the interval to so many small time values, really tiny small values, and this is so small that delta t almost approaches to zero. Okay, that time interval that you have chosen, it almost approaches to zero. Delta x also approaches to zero, but in calculus, when both quantities approach to zero, they reach to a limiting value. Okay, they do have a definite value. That value is defined as the instantaneous velocity. So for us, the instantaneous velocity is limit delta t approaches to zero. Delta t approaches to zero means, it just means that it is very small time interval. It's so small that velocity reaches to one single value, and delta x over delta t. And just know it's more calculus concept, okay, where you want to see the change in one quantity with respect, small change in one quantity with respect to another quantity. So if you have a graph for velocity, and the graph looks something like that, and the average velocity is going to be somewhere in the middle, right? If I don't put any values there, you know that it's going to vary somewhere from 0 to this constant value, because this increase, then constant, increase, then constant. So somewhere in between is going to be average velocity. But what is the instantaneous velocity? If I give this time scale as 1, 2, 3, 4, 5, 6 minutes, then the instantaneous velocity is going to be velocity at each point. This velocity you are talking about. Okay, for some interval, this velocity is constant. For some interval, it is not constant. For example, if you want to do it at maybe 2.5 minutes, is going to end up somewhere here. That is not that will give you one value, but that is at the point where it is increasing continuously. For some instant, it's going to be smaller. So at each and every single point along the curve is the instantaneous value. Okay, so by looking at the curve, we can tell the instantaneous value. Like I said, it's already a calculus concept, so you will not be able to see a lot of questions related, like in terms of solving, that you need to find the instantaneous velocity. Maximum you can see is getting the value for instantaneous speed or velocity from the graph, where at each time you can extend and see what is the instantaneous velocity at the moment. So this is graphically, if you see, um, the point A and B, so I think you might have forgotten the picture that I have here, this one, A and B. So average velocity from A to B, you can draw a line from A to B, and the slope of that line is the average velocity. If you bring point B very, very close to point A, you see the blue lines, you are moving it back, and when you bring it really close to this, here you get a tangent line, and that gives you the slope of the line right at that point, which you define as the tangent line. Okay, this is something that you learned in the lab yesterday too, where you had a curved graph and you were trying to find the value of velocity at a certain time. What you did there was draw a tangent line. This is that tangent line. If you bring the points too close, the tangent line give you, the slope of that line give you the velocity at that point, graphically. Your speedometer cannot give you the average velocity, because speedometer is not going to wait for an hour to give you the speed as 75 miles per hour. Right? You see value all the time on your speedometer. As soon as you start the car, you can see a number there. Where does that number come from? That is the instantaneous velocity. Not velocity, speed. It's not telling you any direction. It's only telling you a number. There are two graphs in this picture. You see the top one is the situation when the object moving with a same velocity throughout. So this is the hour, and the velocity remains 40 kilometers per hour continuously. You can draw a constant line at 40 kilometers per hour. In this case, will instantaneous velocity be different from 40? No, it should be the same, because that is the speed throughout its motion. Here, it is moving in one direction, velocity is increasing, velocity becomes constant, velocity decreases, velocity becomes constant, velocity decreases again to 0. On average, if you sum all the value over the interval, you can find this interval, this interval, this interval, and you sum all the values over this interval, the average velocity would sum somewhere in the middle, right? But instantaneous velocity, let's say at 0.1 hour, the instantaneous velocity would be 50 kilometer per hour. At 0.3, it's going to be 20 kilometer per hour. So instantaneous velocity will vary when the time changes. But the average velocity, if you are looking at the average velocity over a certain interval, that interval can change. You can do the average velocity just over this interval. You can do the average velocity over all interval. Some basic differences in speed and velocity. Speed is the distance covered during that elapsed time. If the object is moving in a straight line, then velocity and speed should have the same magnitude. Okay, if they are not in the straight line, then they could be different. Speed is a scalar quantity, velocity is a vector. They both have exactly the same units. Average velocity can be 0 if you return to the same starting point. Average speed could be equal or greater than average velocity. So you take your car out of the parking lot, you drive it for next 5 hours for about 30 kilometer distance. And you bring the car back, and luckily you get the same parking spot. You park at the same spot. What would be your average speed for your trip? Did you get the question? Sorry? Total distance, 30 kilometer, 5 hours, 6 kilometer per hour. Might? Good? Agree? What would be the velocity? Yes?
Are we driving at 30 kilometers over a 5-hour trip?
Yeah. What would be the average velocity over that interval? The same? There could be direction. So, if you bring it back to the same spot and you are doing the average velocity over this interval, when you have brought it back to the same spot, the average velocity will be 0. Okay, average speed is not 0, but average velocity for that interval would be 0 because your displacement is 0 at the end of your trip. How interesting. Okay, so direction doesn't really play any role there. If you have brought it back to the same point, the displacement is 0. You throw something upward, the time it takes to come back, if it gets caught at the same point, your displacement is 0. It didn't have any velocity at all. It did have a speed because it has covered the distance. So there are very important distinction that you have to make between these two quantities, because if there is an average speed, not necessarily there is an average velocity too. Very interesting example that will help you understand more for these two quantities. During the 30-minute round trip to the store, the total distance traveled is 6 kilometers. 6 kilometers, it's a round trip. So that means 15 minutes to go, 15 minutes to come back. And total is 6 kilometers. So that means one way it's 3 kilometers per hour. The displacement for the round trip is 0. So there was no net change in position. The average velocity is 0. Can you go ahead and draw the graphs for position? How did the position change during that trip, speed and velocity? Draw it on your paper. Back and forth from store to the house. Every time you should have time on x-axis. So what I want from you is this. Time, position, time, speed, and time velocity. That's right. It comes back too.
Okay. Oh, it said it in 15 minutes ago on there. So
Halfway.
half hour.
The whole thing, yes. So half hour, then it would add just one more line to it. Do it for the whole trip, going to the store, coming back from the store, but use the same numbers. Who trusts your answer? Anyone who really trusts the answer and want to share? There gotta be someone. That speed? That speed? Okay. What about velocity? Okay. So you're not plotting average velocity, you're plotting velocity. You see what I mean? Yeah, average velocity is 0, but you're not plotting average velocity here. Average velocity plot, yes, it's going to be a 0 line. Yes. So when it's going towards the store, it's getting away from it, that means it's going up. Okay, when it's coming back, that means the distance is decreasing, it's going down. And follow the same thing for the velocity. Mm-hmm.
Okay, so how do I know that?
Because from when it's going, so this is the house, this is the store.
Mm-hmm.
It's measuring the position in time. You start your watch, your distance from your house is increasing.
Mm-hmm.
You reach the store, right? Now you're coming back. Your distance with the house is decreasing.
Okay. So I have to put any numbers on.
Yes, you can put the number. It takes about a quarter of an hour to go to the store, and the distance would be 3 kilometers. Okay, so you could take the 3 kilometer on this axis, time on this axis. I know the first one, most of you did get that. The first graph, position versus time, you see that when it is getting away, so I don't have the picture of the actual problem. We are still doing this. There is a house, there is a store. You walk away from the house, that means the position is increasing in time. Okay, for quarter of an hour, it goes away from the house and covers 3 kilometer distance. So you see that it has covered in quarter of an hour, it has covered the distance, and then it is coming back. Below is the velocity, and speed is constant throughout. And someone said the average velocity is 0. You're not plotting average velocity here. If you're plotting the average velocity here, then it's going to be a constant line at 0, because average velocity, if you average this and this, what is it going to be? 0, right? Positive number below the negative number, they all are going to cancel each other out. So initially the velocity is this, then the velocity when you're coming back is this. So when we can put them together, there is a discontinuity. So same number of values here and here, positive, negative, you average them out, it's going to be 0. Okay? But conceptually, we also know that this value for average velocity over the trip, because the displacement is 0, it is going to be 0. But average speed is not 0, it remains at a constant value. Yes? Mm-hmm. I know, but this problem is only talking about the distance going and coming back. And it doesn't say anything about it, how long did it stay there. Yes, if you could see a problem where this can add to the same problem, that it spent this much time at the store, right? And then the problem would be different. But in this problem, you are not interested what's happening in the store. You are just interested looking at what happens when it goes away and towards the house again.
But if it did say that they spent X amount of
You
time
will have
before-
to include that time. Yes, yes. You know, the speed was 0 during that time. And the whatever was the time when you stayed there, maybe 30 minutes shopping time, and then came back. Yes, it will be included in that. All right? A commuter train travels from Baltimore to Washington, D.C. and back in 1 hour, 45 minutes. The distance between the two stations is approximately 40 miles. What is the average velocity of the train and the average speed of the train? Try doing that. Take a separate sheet of paper, okay, that you can leave with me. Give me your answer in miles per hour. So that means you want to convert this 45 minutes to hours. We are here. This is the chapter we started. How does it work? We did this today. We haven't done this yet. We are on this topic. Okay? This is university physics. You need go back to OpenStax. Same website, but where they have listed all the books. Okay, look for the books. Yeah, this right here. This is college physics. This is what you need. This one, this purple book. And here, we are here. Go up. Here, time, velocity, and speed. Yes. Okay? miles per hour. You can talk to each other, it's fine. Miles per hour. You don't know? Oh, you know. Think about it. The distance is given to you. You want to know average speed. Back and forth trip to the same station. So it goes from Baltimore to Washington, D.C., and it comes back in this time. You want to know the average speed during that trip. You have distance, you have time. It just looks complicated because you have put the number and the words together, but it's fairly simple problem.
Does this look right? Did I do my definition of average velocity right? And it tracks? Okay.
Perfect.
Thank you.
But average speed, do the average speed too.
Okay, I'm going to do the average speed.
Yeah.
I find that's easier.
Yes. 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 So, yeah, velocity is fine. Yeah. Yeah, 40 miles twice. Good. You got that.
The average velocity of the train, are you just talking about the train going straight to...
So there are two stations. It starts from here, goes to the other station, comes back to the same station.
Right. So we're talking about the train traveling from both stations?
Both stations. No, train starts from one station, goes to the other one, comes back to the same station.
Same spot.
Same spot, yeah.
Does that mean that average velocity is just 0 because it's just traveling up straight?
Yeah.
All right.
I'll comment over you already. So if it comes back to the same station, that will be 0.
Yeah.
Okay.
Because displacement is 0.
Okay.
Right?
And I forgot how to find the average speed.
Average speed is the distance over time. See? So displacement or distance over time.
Oh, okay.
Miles per hour.
For speed? Okay. I was like,
I see you have gone already quite far here. Almost everyone got the idea. You have to convert the time to hours. That gives you 1.75 hour. And what's the total distance covered? Is 80 miles. And for average speed, speed is always distance over time. It's going to be you just divide these two numbers. That is going to give you speed. You don't put any vectors anywhere because we are not dealing with vector quantity here. Miles per 1.75 hour. You can divide them, you can get the answer. Average velocity, since it's a back and forth trip. Now, it's not always going to tell you like it's come back to exactly the same spot, like I described using the parking spot example. But when it says back and forth and comes back to the same station, that simply means there is no displacement. All right. Otherwise, it would have made it very clear that it is there must be some sort of displacement in two positions. So average velocity would be 0, just like this. So fairly simple problem. You always have to know if you do not know how did the acceleration, so we haven't done the acceleration yet, that would complete the picture. But if you don't know how the acceleration or how the speed is changing during the trip, you always need to know the total distance covered and total time taken to cover that distance to calculate the average speed. This one is also a similar problem. We're not going to do it here. You can just write it down, try doing it at home yourself. So there is a helicopter blade which spins about 100 revolutions per minute. Its tip is 5 meters from the center. So radius is given to you. Calculate the average speed of the blade tip in the helicopter frame of reference. You want to know how much it will cover, the blade tip cover in 100 revolution trip. And what's the average velocity over one revolution. So that means it completes one revolution, one complete round trip. Can anyone give us any bright ideas how to go about this problem? Yes. Yes. Find out. That's 100 revolutions per minute. So you will find out how much distance has been covered in 100 when it goes 100 times. Right? You will multiply it by 100. Whatever distance you have measured, you will multiply it by 100. That will give you the total distance covered in 100 revolutions. Then you will divide it by, is the time given? One revolution. Okay, so then you will get the time per second. And the average velocity over one revolution would be what? 0. Okay, because if it's revolving, it starts from here, it completes one trip and it comes back to the same point. One revolution, exact one round trip, it's 0. Velocity is 0 in this problem too. All right, good. All right. Let's move on to acceleration. When the position is changing, you have the velocity or speed. When the velocity changes or speed changes, you have the acceleration. Okay, I see something. There is a typo on the slide. Both show as VF. One should be initial velocity, VI. So change in velocity over time is acceleration. Change in displacement over time is velocity. If velocity remains constant, there is no acceleration. But if the velocity changes, there will be acceleration. A is called the average acceleration, again, because you are averaging it over time. V is the velocity, T is the time, the unit is meter per second square. Since it depends on the velocity and velocity is a vector quantity, this is also a vector quantity, meter per second over second, meter per second square.